So we can get started. And the first thing I'd actually like to do before I introduce our speaker is to just actually take a moment to comment, to essentially thank you all for responding to the survey that we sent out a couple of weeks ago. Actually, the survey link is still live and we're still accepting input. But I thought I would just briefly mention that we got responses from quite a number of you, and a couple of things that came out. We were really happy to hear that overall our speakers have been doing a fantastic job pitching the talks at the right level. So I think 96% of you said the level of the talks is just right. Many of you have been happy with the range of topics, but there was also some input that it would be nice to have occasionally also broader talks, maybe colloquium style talks that address adjacent areas that we aren't covering yet. And so that's something that we'll be keeping in mind as we go forward and continue the programming beyond this summer. As you hopefully have seen on the website, we already have an exciting set of talks lined up for the coming weeks. One other thing we asked about is if we gave an opportunity for post-seminar discussions with the speakers, so going beyond this sort of one-way webinar format to having really an interactive discussion in a Zoom room where students can directly talk to the speakers. We got quite an enthusiastic response that over 70% of you said you would either occasionally or even regularly participate in such discussions. So in light of that, one of the first things that we're going to be trying in response to your comments is starting today, after the seminar, we will be having a discussion with our speaker in a separate Zoom room where everybody is welcome, faculty, students. We particularly encourage students and postdocs to participate. And going forward, we'll also potentially be looking for students or postdocs who are interested in helping to moderate these discussions. So this is a bit of an experiment, but essentially the way it will work is that at the end of the formal talk, we will be posting a link to a separate Zoom room inside the Zoom webinar. Okay, so you need to be in the Zoom webinar. If you're watching from YouTube, you might consider switching into the Zoom webinar so that you'll have access to that link in order to participate in a discussion after the seminar. So I hope that many of you will join that. It's an experiment today, and we're really eager to see how it goes. One other thing that came up is that you reminded us that we should do a better job encouraging questions from students during these talks. We're always really eager to get questions from students. In practice, often the total number of questions we get from students is approximately equal to the total number of questions we get from Bill Phillips. And we love Bill Phillips' questions, but we also want to hear from students. And I know sometimes you're concerned if you type a question into the chat before the speaker pauses, maybe the speaker will answer your question by the time the pause comes. Don't worry about that. Type in questions as you think of them. Our moderators are really doing their best to kind of also filter, and if a question was already answered, they won't ask it. But we'd really like to have your questions to draw from, particularly questions from our student and postdoc listeners. So obviously I couldn't address every comment that came into the survey, but we've been reading them and will be acting on things you told us going forward. So with that, I will now stop sharing so that our speaker can start sharing his slides. So Dave, you can start setting up your slides. And meanwhile, I can just tell you that our speaker today, we're very fortunate to have Dave Demille, who's professor of physics at Yale University. Dave is a world leader in the field of precision measurements of fundamental physics. He's also a pioneer of the rapidly advancing field of laser cooling and trapping of molecules. Dave is a fellow of the American Physical Society for his achievements in the field of precision measurement. He's been recognized by the APS's Francis Pipkin Award. And we're very happy that today he will be telling us about recent advances in that area using molecules to explore discrete symmetry violations in nuclear and particle physics. And so with that, I will hand it over to Dave.
Great. Well, thank you for the nice introduction, Monica, and thanks to all the organizers for putting this together. It's really really been a tremendous series, and it's an honor to be speaking here. So can I just get a check from Monica? Are you able to see my slides and my pointer now?
Yes.
Great. Right. So today I'm going to be telling you about a few pieces of work in our group where we're using molecules to explore discrete symmetry violations like parity violation and CP violation, where the goals are really to address questions in nuclear and particle physics, but the methods are pure AMO. Just quickly, I'll give you a brief overview of how we can use atoms and molecules to detect signals from nuclear and particle physics. Then some specifics about our experiment to measure a certain aspect of parity violation, then quite a bit more about current and future experiments to look at CP violation using molecules in particular. So just in today's world of quantum devices being the paradigm that everybody likes to think about, it's worth realizing that the atomic clocks are really the original quantum technology. They started back in the 50s, and they, of course, provide the most accurate physical measurements of any type. And I'll just motivate some of what comes next by pointing out that the state of the art in atomic clock technology was still thermal atomic beams up until the late 1990s. So the tremendous progress that most of you have seen during your scientific lifetime in clocks using laser cooled and trapped atoms and ions is really a relatively new technology. So with that in mind, much of what I'll tell you about is finding ways to cast measurements of discrete symmetry violations, parity and CP violation, in terms of a frequency measurement or equivalently an energy or time or phase measurement. And in all of these experiments, there's a certain figure of merit for statistical precision, much like is the case for clocks. There's some overall intrinsic sensitivity factor called Q. You want that factor to be large. You want the coherence time of some quantum superposition state to be large, the analog of clock states. And then you want good statistics to get excellent signal to noise. And of course, in the standard quantum limit, the signal to noise is limited by the square root of the number of particles you detect. Oh, let's see. I am frozen. There we go. So what's interesting is that atoms, and in particular molecules, can be used as transducers for these signals that violate discrete symmetries. And the underlying reason is that electromagnetic interactions completely define ordinary matter. And of course, electromagnetic interactions obey discrete symmetries like parity, time reversal, and charge conjugation. But new or more exotic interactions like the weak interaction or interactions with supersymmetric particles, which may or may not exist, and many other types of interactions that have been hypothesized or predicted in various ways can break these symmetries and induce characteristic energy shifts in humble atoms and molecules. So really the key takeaway here is that these symmetry violating signals, because they're forbidden by electromagnetism, can give what is a background free probe for new physics, so that we're rarely interested in absolute accuracy, but much more often in precision. And there's an asterisk there. You'll see a caveat to that statement in a few minutes. So let me start this first section of the talk by telling you about parity violation. And of course, from the particle physics point of view, atoms and molecules are held together by Coulomb interactions, which are associated with virtual exchange of photons between electrons and nuclei. And this gives rise to atomic states that we know and love that are parity eigenstates. But there is always also present weak interactions due to virtual exchange of Z bosons between electrons and nuclei. And what is quite different about Z0 exchange, the weak interaction as compared to electromagnetic interactions, is that this particular exchange violates or leads to violation of parity. And you can see for the Coulomb interaction, both the electron and the nucleus have some characteristic electric charge. That's a dimensionless number that tells us how strong the interaction between these particles is. For the weak interaction, the electrons and the nuclei actually have two characteristic charges. One of them is called a vector charge that's analogous to the ordinary electromagnetic charge. The other is called an axial charge, which not surprisingly has different parity properties than the vector charges. So for example, the strength of the interaction due to the Z exchange between electrons and nucleons actually has four terms from the product of vector plus axial times vector plus axial, but only the cross terms such as axial electron charge times vector nucleon charge give rise to parity violation. And parity violation means explicitly that S states for a single electron atom are in fact given by superpositions of S state and a tiny little admixture of P states, so no longer parity eigenstates. The amount of this mixing is determined by some properties of the electron wave function and the product of these two charges, the axial and vector charges. The electron wave function is a quantity that we rely on AMO theorists to calculate. And if we can measure this mixing coefficient and we know this electron wave function factor, we can determine this product of axial times vector charges. This particular combination, axial electron times vector nucleon, is known as the weak charge. And it's entirely possible that there are other new particles that haven't been discovered that could mediate similar interactions. For example, just a heavier analog of a Z boson called a Z prime. And if this exists, it's possible that it could lead to a change in this coefficient or this dimensionless number that is different from what's predicted in the standard model. So parity violation is really used as a probe of Z boson properties. And as I mentioned, this atomic weak charge has been historically the most important measurement or most important quantity of most interest. And the general idea of parity breaking is that your atoms or molecules will undergo energy shifts that are different depending on the handedness of their environment, given, for example, by electric, magnetic, and laser polarizations. And this is, in fact, the basis of the experiment, the conceptual basis of the famous experiment in Carl Wyman's group, preceded by lots of beautiful work in several other groups. But this was so far the most accurate type of parity violation measurement, published more than 20 years ago now, that used a beam of cesium atoms subjected to a perpendicular set of electric and magnetic fields and laser helicity. So with this technique, Wyman's group was able to measure the weak charge to, which is a non-zero number, and they measured it to an accuracy of about 0.4%. Atomic theory groups, several of them working together and independently, were able to interpret this with 0.3% accuracy. That is, they calculated the electron wave function factor to that accuracy. And so altogether, this roughly 0.5% knowledge of the weak charge tells you lots of novel information about the properties of Z bosons. Here, for example, is a recent plot of the impact or how this cesium atomic parity violation measurement compares to measurements done at accelerators that operate at much higher energies. And you can see the accuracy is quite comparable and in fact better than many of these measurements. So the results of this is that the weak charge that was measured by Wyman's group agrees with the standard model. Even 20 years later, it's providing interesting constraints on new physics from Z prime bosons. The trouble is it's no longer background free, so that in order to make progress, you need both a measurement technique and calculational techniques on a system that can get you to well below 0.5% accuracy. And so far, there's nothing clearly on the horizon to do that. What we're doing in my group is looking at a second aspect of atomic parity violation, where instead of the weak charge, we're looking at parity violation that comes from the other combination of coupling constants, the electron vector and nuclear axial charges. The reason this has not been studied very much is it's so tiny, it's hard to measure. So depending on the conditions, this nuclear spin-dependent parity violation effect is 30 to even 1,000 times smaller than the weak charge. And this is called nuclear spin-dependent because it couples to something that looks like an axial vector of the nucleus. And the only axial vector you can form from a nucleus is its nuclear spin. So this ends up looking like a parity violating hyperfine interaction. What's interesting about this is actually very difficult to calculate in the standard model. And it's difficult to calculate because it undergoes a order unity renormalization from strong interactions inside the nucleus. And this is still something that's poorly understood and poorly measured. So this is an opportunity to, if we can measure these sort of couplings, an opportunity to understand how the weak interaction is modified in the presence of the strong interaction. So it's, under some circumstances, could be a very interesting new test of lattice QCD, for example. It turns out there's another effect in addition to this, which is still due to weak interactions. It has to be in order to violate parity. But here the weak interactions are taking place between the neutrons and protons inside the nucleus that deforms the nuclear structure to create a current that looks like a toroidal winding inside the nucleus. This the electromagnetic moment associated with this is called an Anapule moment, and that couples via ordinary magnetic interactions to the electron spin. So this also gives rise to a parity violating hyperfine-like term in the Hamiltonian. And in some circumstances, this is larger. In some circumstances, this is larger. So in practice, what this does is it gives you some hyperfine-like parity violating interaction. The most important thing here is the term that's nuclear spin dotted into electron spin. And the fact that the overall dimensionless coefficient describing the strength of this Hamiltonian is a sum of two terms, the one from direct Z exchange and one from this nuclear Anapule moment. Let's see, I'm frozen for a second, hopefully only for a second. There we go. So this interaction, Hamiltonian, gives rise to matrix elements between even and odd parity states, nominal even and odd parity states, which is, again, some electron wave function factor that has to be calculated, times now a sum of two dimensionless couplings, which this one about Z0 exchange tells us something about how QCD modifies the weak coupling to nucleons. And this other one, the Anapule term, tells us how weak interactions inside a nucleus are, how strong those are. And this electron wave function factor is proportional to the atomic charge Z squared. So this is much bigger for heavier atoms or molecules. The next terms, which I don't know why I keep freezing here, but let's try it again. The next terms, oh, that's not good. Okay, I'm going to try to restart my PowerPoint since that just crashed on me. Give me just a second.
We can be patient. I'm happy to see that We're starting to have at least one question typed into the Q&A here. I can use this as a reminder to please type your questions for Dave into the Q&A if you're in Zoom, or into the YouTube chat if you're watching by YouTube.
And let me add, while I get things set up here, that I will be very happy to have questions from students and other audience members. Hopefully I have a talk to show you.
And if the talks doesn't work, we can just convert this to an open-ended Q&A. You know,
Yeah.
there are always backup options.
Yeah.
Or a sing-along. Monica's like, yeah, we're not doing a sing-along.
A solo performance. Yeah.
I mean, if you want to, Monica. Or is that not the implication?
That was not the implication. Okay.
Okay, are you able to see my screens again? Or my slides again? I'll take
Yes.
that as no.
Yes.
Now we can.
Okay, great. Right. So as I was saying, this new effect of parity violation that we're starting to study now, this nuclear spin-dependent parity violation, effectively mixes even and odd parity states with a strength that grows like Z squared. And then the two underlying interactions, the Z boson exchange and the nuclear anapole moment, which has to do with weak interactions inside the nucleus. Wow, is this going to crash on me again? Okay, yes. Not sure what is happening here. My PowerPoint seems very unhappy.
Another option, if it continues to be unhappy, is that you send one of us the slides and we flip slides for you. That is suboptimal, but I think we have options. So. Yeah,
I think what I might try to do is, it seems to be something about the presenter view, or the slideshow view. So I'm going to try it without that. It won't be quite as appealing, but okay, let us try this now.
Would you like us to ask some questions now while you get things up and running again?
Sure, that would be terrific. Yeah.
Okay, so let me start with a question from Dan, actually, which is what's going on with the LHC results at very high Q? There seems to be a substantial disagreement there with the lower Q results, and also with the low energy experiment result.
Right. So I hope you're seeing this slide now, but yeah, this is just a weird choice of displaying. The LHC data point should actually be translated over to in between these two arrows. So it's completely in line with all the other results.
But all of those numbers, I see. So, but it should fall off with Q, is the point.
Well, yeah, it falls off with Q until it hits this energy, which is the equivalent to the mass of the Z boson. And then it starts heading in the other direction at energies above the mass of the Z boson. which is, yeah.
Okay, great.
Just a
Another
feature of how-
question.
Mhm.
Perfect. This is from Ariane Jadbabi. And the question is, why is the matrix element of parity violation imaginary? He thought that imaginary terms were odd under time reversal.
Yes, that's a very excellent question. So it turns out that that term is pure and imaginary exactly because of time reversal and variance. It does seem surprising that that should be imaginary, but if you think about it, you're used to perfectly ordinary Hamiltonians having imaginary off-diagonal matrix elements. If you think of a Pauli matrix like sigma y, that always has pure imaginary off-diagonal matrix elements. So that in and of itself doesn't have anything to do with time reversal violation. The presence of pure imaginary matrix elements. But in this particular case, the fact that the Z0 exchange process conserves time reversal forces those to be pure imaginary. I don't have a great explanation for that, but that's the case.
Let's do one more for now. Bill Phillips asks, I think that's an undergraduate, right? Bill Phillips. Bill asks, do the interactions that lead to an Anapule moment also lead to a nuclear EDF?
No, these are ordinary weak interactions between protons and neutrons in the nucleus that give rise to the nuclear Anapule moment. They're weak interactions that are completely modified in strength by the strong interactions between the protons and neutrons in the nucleus, but there's no exotic new physics. It's pure parity violation, independent of time reversal violation.
Great. Shall we move forward?
Yes.
Great.
All righty. So as I was trying to say, and hopefully this will work for a while now, the Anapule moment term also grows with Z, whereas the Z exchange term does not. So heavier nuclei allow you to measure Anapule moments, lighter nuclei allow you to measure this Z exchange term. So what we're really after here is measuring this Z exchange term, this nuclear spin dependent term that is not from an Anapule moment, will allow us to understand new things about how Z couplings are modified by strong interactions, QCD in particular. And the nuclear Anapule moments will tell us about parity violating couplings between nucleons, which despite 50 years of effort in the nuclear physics community are still quite poorly known. And really the best way to fix this is to develop a table of Anapule moments of many different nuclei. It's a unique property of each nucleus, much like the magnetic dipole moment or the electric quadrupole moment of nuclei is a unique feature of those nuclei. And so far, we have only one measurement of an Anapule moment from Carl Wyman's experiment that I mentioned before. Unfortunately, the result from that disagrees completely with the theoretical predictions. So there's still a lot of confusion about what's going on there. So let me tell you a little about the experiment that we're doing to measure this nuclear spin-dependent parity violation. We call the experiment Zombies, staffed by an excellent group of graduate students and postdocs. This is the full historical list. The results I'll tell you about were done by Sid Khan and M&A Altuntash. So the reason that molecules are good to look for parity violation is, as I mentioned, we're ultimately trying to measure some mixing of even and odd parity states due to a weak interaction, a parity violating interaction. And ordinary perturbation theory tells us the mixing coefficient is a matrix element divided by an energy denominator. The splitting between rotational levels in molecules, which have opposite parity, is about 4 orders of magnitude smaller than the splitting between S and P states in atoms. So this mixing is naturally 4 orders of magnitude bigger in molecules than it is in atoms. But we can do even better if, this is going to be sad because I don't have my animations working, but let's try that. So we can do even better than the bare rotational splittings by applying a magnetic field of the order of a Tesla. We're able to bring two opposite parity levels to almost exact degeneracy. In this case, in practice, we're able to get these levels down to order of kilohertz apart, which gives us an 11 order of magnitude enhancement in this energy denominator compared to the classic experiments like Wyman's experiment. So this is a really gigantic enhancement of the effect that we're interested in. The way we do this in practice, we have a beam of molecules that travels from left to right in this picture. All my animations are broken, but we'll see if this works. As the molecules travel from left to right, they enter a superconducting solenoid that creates a magnetic field tuned to create a level crossing, as in the previous picture. They then encounter a laser beam that optically pumps out, for example, the even parity state. They then enter a region of electrodes, and as they fly through the electrodes, they see a spatially varying electric field, which in their frame looks like a temporally varying electric field. And that field plus the weak interaction causes some of the population to transfer into the previously empty state. Then at the end of the whole business, we have another laser where we detect the population in that previously empty state via laser-induced fluorescence. So just to zoom in on what happens in the interaction region here, as the molecules, when they're outside the magnet, their energies or the opposite parity levels are order many gigahertz apart. When they get into the central homogeneous region of the magnet, their energies are now only order a kilohertz apart. And when they're in that condition, we apply a single cycle oscillation of an electric field. With apologies, a little math to describe this. The whole thing is, because it's a two-level system, you can write a simple Hamiltonian. Everybody knows how to diagonalize this. And if you go through that simple procedure, you find that the population in this originally empty level can be written as terms that have one part which is proportional to the square of the electric field that the molecules feel. And then another term which is an interference term between the weak interaction and the electric field. So this difference is really explicit parity violation. It allows us to determine what W is, which is where all the interesting physics lies. Also worth pointing out that the fact that this W is pure imaginary is very important here, in the sense that if the electric field were just a static electric field, when you diagonalize this Hamiltonian and take the mod squared of this matrix element or complete Hamiltonian entry, you'll never get interference between the weak interaction and the electric field. So we're able to fix that by using an oscillating field rather than a static field. So we measure this signal from the equation on the last slide. We do it first with an electric field that begins in the positive direction, and then again with an electric field that begins in a negative direction. Then we take an asymmetry, which is the difference of those signals over their sum, and do a little algebra, and you find that this asymmetry is proportional to the matrix element that has the physics of interest, W. It's also proportional to other factors that are under our control and well known. And this all has a dispersion-like feature as a function of the detuning between the levels. It's also interesting is if you work out the statistical sensitivity of this, you get an expression which is essentially the same as the expression that you would get for measuring an energy shift in a clock-like system. And that's no accident. It was pointed out back in the 90s by Norval Fortson that this sort of measurement is equivalent to the measurement of an AC Stark shift. So like any other energy shift measurement, you want a long interaction time and lots of statistics. So to make a long story short, we've done these measurements in a test case in the barium fluoride molecule with a spin 0 barium nucleus, but a spin 1/2 fluorine nucleus. This is really a proof of concept run because the fluorine is so light that we didn't expect, we knew we couldn't possibly be sensitive to the small effect from fluorine. So we knew that if everything was working right, we would get a result of 0 here. And indeed, we got a number that's consistent with 0 with an uncertainty of about 2 Hertz. If you compare this to Wyman's experiment, this first test case run is already 7 times more sensitive than Wyman's old cesium experiment. And we're now putting in some extra upgrades to allow us to make a measurement on barium 137 by improving the statistics, where we expect the signal to be not at all 0. This technique looks like it can generalize to be able to make measurements of many nuclei in the periodic table shown in the colored dots here. So we don't know how to measure every nucleus, but it looks like this technique could be used to build up a big table of nuclear anapole moments going forward. Okay, so I'm going to pause there and shift gears. Maybe this is a good time for a couple more questions.
Let me unmute myself. Terrific. Okay. First question from Mehdi Hassan. As you showed the degeneracy after applying a 1 Tesla field, the states become degenerate. Wouldn't the degeneracy be a signal of preservation of symmetry rather than violation?
Yes, that's an excellent point. So in fact, because of the parity violation, there's not exact degeneracy, but rather an avoided crossing as you change the magnetic field through 0 detuning, essentially. But that energy splitting, the avoided crossing, will have a splitting that's only this matrix element W, which is on the order of a Hertz. So unless you have energy resolution that's better than a Hertz, you won't be able to detect that avoided crossing. What the Stark interference technique allows us to do is to measure a matrix element that's much smaller than the actual energy resolution in the system for a single shot. But in principle, you could measure that avoided crossing if you had a system with long enough coherence time.
Okay, here's another question from Mohit Verma. Why barium fluoride as opposed to a heavier molecule like ytterbium fluoride? Does the anapole moment get larger with Z?
It does indeed. And this was a choice driven by history many, many years ago. Barium fluoride was chosen because it was known how to make beams of it, and the lasers for it are all diode lasers. So it was relatively easy to set up the lasers for the system. In retrospect, if we were starting from scratch, we would definitely use a different species, which would be easier.
Thank you. One more question for you from Aruku Sanu, who couldn't quite get what the difference was experimentally between the weak charge-induced shift and the nuclear spin-induced shift. Can you clarify that in a few words?
Yes, let me see if I can get this signal back. So the idea is that for the weak interaction, there are actually 2 different kinds of charge for each type of particle. So the electron has 2 charges, a vector charge and an axial charge. The nucleons have 2 charges, a vector charge and an axial charge. By analogy with the Coulomb interaction, the strength of the interaction depends on the product of the 2 charges. So the strength of the weak interaction depends on the product of this vector plus axial electron charge and this vector plus axial nucleon charge. When you multiply those 2 terms together, you get 4 terms, but only 2 of them violate parity. Only 2 of them have the property that's the vector times an axial vector. One is this weak charge, which is the vector nuclear charge times the axial electron charge. The other gives rise to this nuclear spin dependent interaction. That one comes from the axial charge of the nucleon times the vector charge of the electron. So yeah, I hope that answered the question.
It did. And I think in the interest of time, we should move forward here. Thank you very much.
Great. All right. So now I'm going to tell you about a different set of experiments where we're looking not just for parity, but for parity and time reversal violation. So the idea is that if a particle has a charge asymmetry pinned to its spin axis, as shown in this cartoon picture, if you make a time reversal transformation, the spin changes sign, but the static charge distribution doesn't. So if all particles, like all electrons or all protons, look like this, none of these time reversed versions exist because the spin and dipole moment or spin and charge asymmetry flip sign relative to each other. That means time reversal is not a good symmetry of nature. Similar argument shows that this also violates parity symmetry. But really the new part of this is the time reversal violation. In relativistic quantum field theories, the combined symmetry of parity and time reversal and charge conjugation, which means turning particles into antiparticles, is always conserved. That means that if T is violated, then it must be that the combined symmetry CP is also violated in the equal and opposite amount to keep the total CPT symmetry preserved. So particle physicists usually think of T violation as in terms of CP violation, so that's the language I mostly use. And this is a particularly interesting place to look for new physics because we know there must be CP violation beyond what's been measured so far. We know that it's needed in order to explain the asymmetry between matter and antimatter that's observed in the universe. So much like was the case for parity violation, here there are interactions caused by new particles that can, and even by existing known particles that can give rise to CP violation. For example, there can be some new particle that mediates a CP violating force between electrons and quarks in a nucleus. There could be new particles that enter in loop diagrams in an electron, much like the diagrams that give the electron a non-zero G-2 factor, but with the addition of some CP violating interaction. This will give the electron an electric dipole moment along its spin. And the same thing can happen for nuclei and the quarks inside the nuclei, where new types of interactions, for example, from new Higgs bosons, can give rise to a nuclear charge asymmetry called a nuclear shift moment. What's common about all of these things, and this is one of the points I'm trying to make, is that these are all in fact very similar to each other, is that in all cases, an electron-electric dipole moment, a nuclear shift moment, or some CP violating interaction between electrons and nuclei, all have the same effect. So as an example, look at the electron-electric dipole moment. If there's a dipole moment along the spin, which is pointing down in this case, the part of the electron wave function that's on top of the nucleus will on average be repelled from the nucleus because the plus charge of the dipole is closer than the minus charge. So the electron wave function will tend to push away from here. On the bottom of the atom, the electron wave function will tend to be drawn in towards the nucleus because the negative charge of the dipole is closer to the nucleus. That will give you a deformed electron wave function, roughly like this egg shape, which is a charge asymmetry along the spin of the atom itself. And similar effects happen for these other underlying physical causes. Now this means that atomic S states again get mixed with atomic P states with some mixing coefficient, which we would like to measure. This also grows rapidly with atomic number, roughly a Z cubed. And not surprisingly, this doesn't give any energy shifts to first order. There are no diagonal matrix elements between S states or P states, only off-diagonal matrix elements between opposite parity states. This, in fact, doesn't look that exotic. It looks exactly like what you would expect if you put an atom in an electric field, where an external electric field mixes S and P states. The wave function that is an admixture of an S state and a P state gets constructive interference on one side of the nucleus and destructive interference on the other, giving the same sort of egg-shaped electron wave function. And much like the CP violating interaction, there's no first order energy shift due to an electric field. And you can think of this effect of the electric field as inducing an electric polarization. And I'll describe that in terms of a dimensionless number, which is the induced dipole moment of the atom divided by the dipole matrix element between S and P states. So again, if we have a simple toy system with just an even and odd parity state, like an S and P state in an atom, we again get a 2x2 Hamiltonian, something simple enough to diagonalize by hand in a few minutes. And the bottom line here is that the energy shift due to the CP violation has the form, after you go through a little algebra, that it is proportional to the electric polarization of the system, proportional to the electric field, and proportional to this matrix element of some CP violating interaction. The polarization is, again, a dimensionless number. When the electric field is weak, it's weak, meaning D times E is small compared to the energy splitting, then the polarization is small. But when the electric field is big enough that D times E is large compared to delta, this Hamiltonian ends up giving you polarization, which is essentially unity. Then you fully mix the S and P states. So here, the big advantage relative to old experiments with atoms is that in molecules, you can easily get an electric polarization, which is of order 1. Whereas in atoms, even with the biggest fields you can apply, 10 or 100 kilovolts per centimeter, you can only get a tiny electric polarization, 10 to the minus 3 or 10 to the minus 4. And it's simply because energy levels in molecules, like rotational levels, are so much closer together than they are S and P states in atoms. So the way this works in practice is conceptually pretty simple, though it's going to be awful without animation. So let me again try to get animations. Can you see this now? Okay. So if you start with some unpaired particle with spins, let's say, for example, electron spins, you can apply some optical pumping technique, for example, with circularly polarized light, to spin polarize the sample. If you polarize it to the right, that's a superposition of spin up and spin down. For technical reasons, experiments trying to measure these charge asymmetries like an electric dipole moment apply a magnetic field that creates a Larmor precession frequency omega, or equivalently an energy splitting omega between spin up and spin down. And when you apply an electric field as well, if the particle has a dipole moment along its spin, that will slightly increase the precession rate, or equivalently increase the splitting between spin up and spin down. And then you can simply reverse the electric field back and forth and look for correlated shifts in that energy splitting. The figure of merit here is just as promised before. There's a quality factor that depends on the electric field that's acting on these particles, or equivalently the electric polarization in the system. It depends on the coherence time, that sets the energy resolution, and it depends on the statistics. So same as with clocks, same as with parity violation. What's interesting about this case in particular is it turns out all ordinary particles, like electrons and protons, do have charge asymmetries, like electric dipole moments for the electron and shift moments for nuclei. But in the standard model, those charge asymmetries are incredibly tiny. And this is due to some symmetry of the standard model that causes potential contributions to the CP violation to cancel each other severely. It ends up appearing for the electron only in fourth order perturbation theory, a 4-loop Feynman diagram. The standard model's prediction for the electron EDM is not 0, but it's about 9 orders of magnitude below current limits. So it is indeed background free for a long time to come. This means that any new sort of, or any improvements in sensitivity are purely probing new physics without the need for more advanced atomic or molecular theory. To give a sense of what we can detect with this thing, here's again the sort of cartoon model of how a new particle, shown here in green, can couple to an electron with some CP violation associated with it to give rise to an electric dipole moment. This process is quite analogous to the famous QED loop diagram that gives the electron a non-zero G-2 factor. And it's easy to run through a dimensional estimate of how big an electron EDM gets induced by this. It scales like 1 over the mass squared of whatever this new particle is. And it scales like the sine of this dimensionless phase phi that describes the strength of CP violation relative to not CP violating forces. So with reasonable assumptions here, what you find is that the current limit for the electron EDM is already probing particles with mass up around 30 TeV, which is well beyond what you can get at the Large Hadron Collider. So let me tell you about our Acme experiment, which now gives the best limit on the electron EDM. This is a collaboration between my group from Yale, the groups of John Doyle at Harvard, and Jerry Gabriels at Northwestern. So here we take advantage of the fact that there's a large polarizability, or in other language, a large effective electric field inside polar molecules. We use the thorium oxide molecule, which is especially easy to polarize and has an especially high Z atom, thorium, in it. The bottom line is that in this system, the high polarization means that it is as if the valence electrons in this system are experiencing an effective electric field of 80 gigavolts per centimeter, which of course is much bigger than you can apply directly in the lab. And this is now known from molecular calculations to roughly 5% accuracy. And again, the point is that having electrons in a molecule gives you 3 to 4 orders of magnitude larger energy shifts than in atoms. So here's a quick overview of how Acme works. It's again a molecular beam experiment. We start with a cryogenic molecular beam of thorium oxide molecules. They go through a series of optical pumping interactions that cool the rotational motion. They enter an interaction region where a laser optically pumps the ground state molecules to a metastable triplet state where they're unpaired spins. Then another laser spin polarizes the molecules. Molecules then fly freely through a region where there are parallel electric and magnetic fields, as I described before, for about a millisecond or 20 centimeters. And then the spin direction is detected via polarization-dependent fluorescence and collected into photomultipliers. So we now have our first generation of Acme set the best limit on the electron EDM. We went on to do a second generation where we improved the signal by having a larger detection region, by moving from optical pumping to coherent state preparation, and then by doing more efficient detection. The apparatus is a large molecular beam apparatus. You can see some of the pieces here. Here's our magnetic shields and magnetic coils and LHC units for the particle physicists. And it looks like a typical AMO experiment with lots of optics and electro-optics. In the end, what we do is we measure how much the electron spin precesses while the molecule is in the parallel electric and magnetic fields. We set the parameters of the experiment so we get some signal which will go up and down a high slope of what is analogous to a Ramsey fringe. And if the electron has an EDM, it'll move up and down this fringe as we flip the electric field in the experiment. In the end, precision measurements like this, the end product is an error budget like this. Just pointing out here that the systematic errors or systematic shifts that we were able to determine are small compared to the uncertainties in the systematic shifts, meaning our ability to detect systematic errors is limited by our statistics. The statistical uncertainty is a little bit bigger than the systematic uncertainty. And the total uncertainty, about 500 microradians per second, corresponds to an error bar on the electron EDM of 4 times 10 to the minus 30 e centimeters. And the central value is consistent with 0. So this allowed us to set an upper limit that the electron's electric dipole moment is less than about 1 times 10 to the minus 29 e centimeters. This Acme 2 work was done by a fantastic team of students and postdocs shown here. And let me just tell you a little about the particle physics implications of this. So, for example, interactions caused by virtual exchange of some new particles between electrons and quarks in the nucleus set a limit that the strength of this interaction is more than 9 orders of magnitude smaller than the strength of the interaction due to Z boson exchange between electrons and quarks. So these sorts of CP violation experiments are really extraordinarily sensitive, much more sensitive than parity violation measurements so far, but it seems that there may not be fundamental reasons for that. This has had a big impact, for example, on particle theories such as supersymmetric theories. So here's a plot from a particle theorist, Jonathan Feng, that shows on the y-axis the mass of different particles. Here are the 2 heaviest standard model particles, the top quark and the Higgs boson. The lines here in green show what this particular theorist believes are reasonable upper bounds, where if these supersymmetric particles are not found below that mass, then supersymmetry stops making sense. And on the x-axis is all the supersymmetric partners of all the known standard model particles. In blue shown here is the lower bound set by direct searches for new particles at the LHC. This theory paper has the beautiful phrase that all of the constraints shown are merely indicative and subject to significant loopholes and caveats. This is an unfortunate truth that because particle theorists really have no idea what comes next after the standard model, there is no set theory to compare to. So we do our best to make comparisons. This old plot, I updated it recently to show recent progress from the LHC. So the blue lines have moved up as the LHC has taken more data. But it's interesting to compare those to what we learned from electric dipole moment experiments like the Acme experiment. So even the first generation of Acme was already pushing up to near the LHC bounds in some case and above the LHC bounds in other cases for certain types of supersymmetric particles. And Acme 2 has now really pushed our ability to sense high mass particles to well above where the LHC is and actually above where the LHC can ever get. So this is really quite interesting and pushing the boundary of particle physics. So we now have a 3rd generation of Acme under construction where we're using a molecular lens to get more useful molecules. We've extended our interaction region to have a longer interaction time, and we have more efficient fluorescence detection. So the bottom line is that we're expecting a 10 to 20-fold improvement in sensitivity within the next 4 years, give or take. I just want to point out that in addition to the Acme experiment, which sets limits on the electron EDM, there's a long-running, very beautiful experiment looking for nuclear shift moments, which is an analog of the electric dipole moment, of mercury nuclei that are in mercury atoms. It's an experiment that's done at the University of Washington, led now by Blaine Heckel. And this experiment, shown in blue here, is also setting limits on supersymmetric partners that are putting pressure on supersymmetric theories. So point of emphasis here is that there's really complementary information from electron and nuclear EDMs or nuclear shift moments, which really is telling you about physics that couples to leptons versus physics that couples to hadrons. So maybe let me pause there and take some questions, and then I'll get some guidance from the organizers about, yeah, how much longer I should go, given that we're at 4 o'clock, but had lots of troubles.
So I don't have anywhere to be for another couple hours, so I feel like there's really no hurry.
Fantastic.
So let's start with a question from Shankari Rajagopal. Rajagopal, yeah, got it. Would there be any advantage of using trapped molecules for acne rather than a molecular beam?
Yes, that's coming up in the talk, but the
Okay.
answer is probably yes.
Okay, that's one. How about, here's one from Mehdi Hassan. For the avoided crossing due to weak interaction measurement, why don't you do a Landau-Zehner type experiment and try to infer the gap from there?
Yeah, so the trouble is that in order to do a Landau-Zehner type experiment, you have to evolve adiabatically through the avoided crossing in order to tell that there's an avoided crossing there, or close to adiabatically. That means that we need to control the energy level of the molecules at the part per billion level for, in our case, on the order of a second. And right now, we just don't have a way to do that. There's no technology available to do that. But the good news is that our Stark interference measurement gives us the theoretical best case limit of statistical sensitivity, as shown there. So there's really no intrinsic advantage to doing a different measurement technique. Our technique, at least in terms of statistical sensitivity, is the best that you can possibly do. It reaches the standard quantum limit of sensitivity.
Okay, great, thank you. And another one from this Bill character, which is it clear how big the EDM must be to explain the matter-antimatter asymmetry in the universe?
The answer, unfortunately, is no. Again, because particle theorists really have no idea what the new physics is. Of course, there have been many models proposed that would explain the matter-antimatter asymmetry. One of the many appealing things about supersymmetric theories is that they did that in what seemed like a perfectly natural and viable way. But the Acme results have now put enormous pressure, I would say, to a very good approximation, have simply ruled out supersymmetric theories that would have explained the matter-antimatter asymmetry. So apparently there's something else going on, but no one knows what it is. And in some of these theories, the amount of CP violation that would explain the matter-antimatter asymmetry would also lead to an EDM in the next order of magnitude or two. And in other theories, it would only lead to an EDM 7 or 8 orders of magnitude away. So unfortunately, we just don't know.
Great. So I think you asked us for guidance on time. I would say up to 10 more minutes. We would like to try this informal discussion afterwards, and we know you have a hard cutoff. So
yeah, great. So let me just skip to the bottom line here, which is that we've now started a new experiment that we call Centrex. This is a collaboration between my group, Tanya Zelevinsky's group, David Kawal's group, and Steve Lamoureux at Yale, to measure the nuclear shift moment, which is, roughly speaking, the analog to a nuclear electric dipole moment. Here, the idea is that we're going to, again, take advantage of the large polarizability of a molecule that gives us nuclear spin precession rates for the same underlying CP violation that's roughly 4 orders of magnitude faster than in mercury 199 atoms. But what we give up in exchange is we'll have much smaller statistics and much shorter coherence times than the mercury experiment. But there are many things that are known about thallium fluoride, many favorable features about this particular molecule. And the bottom line is this is a new effort to try to improve sensitivity, not to the sort of leptonic interactions that the electron electric dipole moment is sensitive to, but to hadronic CP violating interactions, again, it scales beyond the reach of the LHC. Here's a cartoon schematic of what Centrex, the first generators of Centrex that we're building now, will look like. It obviously looks a whole lot like the Acme experiment. We're taking lots of lessons from that and applying them to this system. And we think this, much like Acme, has a path to future upgrades. For example, thallium fluoride has the right structure to be laser cooled and trapped. So that could give us both more statistics and potentially much longer interaction times for better energy resolution. And Centrex is really being built. Here's the team of, again, fantastic postdoc and students working on this. And just to give you a sense of all the pieces that are going together, this is maybe half of the parts that are going to be needed for the whole apparatus. The bottom line in Centrex is we're forecasting factors of 5 to 20 improvement in some underlying physics, such as the proton's electric dipole moment, quark chromoelectric dipole moments, the strong interaction analog of an electromagnetic electric dipole moment, and a parameter that describes the strength of CP violation in strong interactions. So this is quite exciting, and we're working furiously to get this to come online. Right. So also just mention quickly, all of the state-of-the-art experiments for looking for the electron and nuclear EDMs or equivalents are shown here. Our Acme experiment, the Seattle experiment that's based on mercury atomic vapor cells, and haven't mentioned it, but the GILA trapped molecular ion experiment led by Eric Cornell and Junyi is competitive with our Acme experiment. All of these are very long-running experiments. They've been underway for a decade or much longer in the case of mercury. They're all trying to improve from their latest generation now. But what's sort of striking is these look like very old-fashioned measurements. Molecular beams, vapor cells. The GILA experiment is the first EDM experiment to use trapping to advantage. It's also worth noting that the last 4 electron EDM limits have come from experiments using molecules. So this molecular enhancement has really started to pay off for looking for electron EDM, but it hasn't paid off yet looking for nuclear EDM or nuclear shift moment. But with Centrex, we hope to do that. And as one of the questions already noted, there's a lot of promise from using cold molecules, and even the ultimate version would be trapped molecules to get much longer interaction times and better statistical sensitivity. And of course, that's now possible in many labs around the world. And there are 2 distinct ways to make ultra-cold trapped molecules. One is to assemble them out of pairs of trapped atoms. Of course, this is original work was done in the groups of Debbie Jin and Junyi at GILA, and quickly followed by work in many other groups. And then in parallel, my group and several others have been able to show that direct laser cooling and trapping of some molecules is possible. The techniques for assembled molecules are more advanced. The techniques for direct cooling and trapping of molecules are moving quickly, but still some ways behind in terms of having large samples at low temperatures. But it's intriguing to dream about a situation where if you have molecules trapped in an optical lattice, something similar to what's used now for atomic optical lattice clocks, and put in some optimistic but not insane numbers for coherence time and molecule number, then this has the potential to reach sensitivity that's 1,000 times or more beyond what we've already gotten to in Acme 2. So this is exciting. It's interesting to think which molecules might be good for experiments like that. There are a few requirements, such as a heavy molecule that's easily polarized and can be cooled and trapped. And there are now many different groups who are exploring this for measuring the electron EDM using different molecules and various different techniques. what's interesting is we've now, we meaning myself along with Timo Fleig, a theorist at Toulouse, have identified a way to assemble molecules that actually have very good sensitivity to the electron EDM. And this is very likely not the only example, but it's the first existence proof of a molecule that it seems it should be possible to assemble out of ultra-cold atoms that is sensitive to the electron EDM. Our existence proof is the strange sounding molecule radium silver. So radium is an alkaline earth atom that's the heaviest laser cooled atom. It's been laser cooled for over a decade now at Argonne National Lab. Silver is an alkali-like atom. It has a single valence electron and an s1/2 orbital. It's also the most electronegative atom that's ever been laser cooled. And just to point out, this was indeed laser cooled. A MOT was produced 20 years ago in Herbert Walter's group, and then it was stopped because nobody had a good motivation to do things with silver. Nevertheless, it clearly could be done again, and much like efforts that are ongoing in Florian Schreck's group and elsewhere to assemble alkaline earth alkali molecules, if you could do the same thing for radium silver, actually make a very strongly polar molecule with one unpaired electron spin in its ground state and a very large effective internal electric field, very similar to what's been found in molecules that can be directly laser cooled. This molecule also is very easy to polarize. The bottom line is that this has an effective field almost as big as the one that works in the Acme experiment. And we need a very modest electric field to fully polarize it, around 200 volts per centimeter. So this is, of course, something that's in the far future, but it does give hope that this field is going to continue for a while. And I'll just wrap up by really emphasizing that looking for these CP violating effects, EDMs and nuclear shift moments, is really becoming the new cutting edge of high energy physics in many ways. We already have enough sensitivity to probe scales beyond the direct reach of the LHC, beyond what the LHC will ever reach. And new experiments that are underway already very likely will be able to get another factor of 3 in mass or a factor of 10 in sensitivity. And if those don't give a non-zero electric dipole moment, there are plausible ways to keep advancing in the near future. So, well, yeah, we think this is an exciting time where atomic physics is really going to be a sort of new vanguard of particle physics. So with that, I will end and thank everyone for their patience for the technical glitches.
Okay, so let's take a couple of quick questions here, so that we still have time to have a little bit of a chat offline with Dave before he has to go. Let me just point out that if we do not address your question, it's a perfect opportunity to come join us in the discussion afterwards. So Dave Weiss asks, regarding the campaign to test supersymmetry, if any one of those green lines is well surpassed, is that enough to rule out the supersymmetric theories, at least in a natural range?
Well,
or do they still have wiggle room?
Yeah, as mentioned, this plot has many loopholes and caveats. So this particular theorist's version of what would be natural solutions for supersymmetry. But his version of supersymmetry is essentially a plain vanilla version, which many theorists have been poo-pooing for years as too simplistic. The trouble is nobody knows which extra mechanisms should be added to plain vanilla supersymmetry to make it, in fact, more realistic. But those often change what one would consider natural bounds. What is interesting is the Higgs mass itself. You may be able to see on this slide, the Higgs mass over here with a red line is already so high that it's putting pressure. It's above Jonathan Feng's naturalness bounds. In fact, if you look at what the Higgs mass means for supersymmetry, the most reasonable conclusion that you would draw is supersymmetric particles should have a mass in the range of 100 to 1,000 TeV. So the measured Higgs boson mass actually makes a type of prediction, with loopholes and caveats, but a prediction that really EDMs are essentially the only plausible way to get to that range of supersymmetric particle masses.
Excellent, thank you. And then Shimon asks, do the recently reported observations of CP violation in neutrinos by the Super K experiment imply anything about CP violation in electrons in the electron EDM?
Yeah, so the answer is a definitive maybe, but probably not. So of course it's extremely tentative, but in some sense it would be expected for their experiment to see CP violation from a purely standard model source, very well, completely analogous to the one that's already known from measurements in K mesons and B mesons decades ago. But instead of coming in quarks, this particular mechanism comes in neutrons. If it's just the standard model explanation, which seems likely, then it has really no impact on electron EDM or other EDMs at all. Yeah, unfortunately.
Thank you. Okay, then one last question from Peter Reynolds. Do we know that radium silver is actually a bound molecule?
Well, I certainly didn't know that before, but Timo Fleig is a real expert in these calculations, and he tells me that the sort of hand-waving arguments that I made for why it should be seem to be borne out by detailed, many-body ab initio calculations. The binding energy is it's bigger than a typical bialkali. And the thing is extremely polar, as I would have expected from the large electronegativity of silver. So of course we'll be thrilled to actually see it. It's all calculation at this point, but apparently it does exist, or could.
Well, with that, I think we should wrap up, and we are going to still, I think somebody is sending right now a link to a room for the post-seminar discussion that I hope many of you will join. But meanwhile, let's thank Dave again, and allow me to briefly announce next week's talks. So next week, our speaker in the Friday AMO seminar will be James Thompson from Chile. And our sister series, the Quantum Science Seminar based in Europe, will be featuring Olivier Pfister from the University of Virginia. So tune in for those talks next week. And right now, you should all have a link to a room where we can have actually a two-way discussion with Dave. And so I hope that many of you will join us there.